Geochemical data interpretation can be complex. However, that should not prevent any geoscientists from firing up software and to start looking at their data. Understanding the essential principles of geochemistry, how and why elements are located where they are today, and performing rigorous QA/QC should put you in a great position to looking at your data with confidence. Geochemists tend to have go-to plots and a general workflow of looking at data that is born from experience of working in specific systems. So that said, let's talk about some plots. Exploratory data analysis, or EDA, is a process of iterative learning whereby geoscientists analyze geochemical data to look for trends and structures that provide insight to geological or geochemical processes. Remember, geochemical data has a spatial component. Some issues that you can see with geochemical data when doing exploratory data analysis are that data can be above or below detection, you can have non-normal distributions, missing values, combined groups of data that have inconsistent digests, instrument finishes, or analytical laboratories, wrong coordinates, and also the constant sum problem or closure. At the top right here, we are looking at the results of a discriminatory projection analysis, whereby we're looking to classify different branches using geochemistry. The groupings here, they look compelling. However, without checking the spatial component like we've done below, the results are meaningless. So it's really important to always check that spatial component. Before interpreting geochemical data, the data almost always needs to be mathematically transformed to more normal forms so that the underlying statistical assumptions are met. For geochemical data, we almost always use a log transform. Note that it's not always appropriate to blanket apply a log transformation. So for example, here, you're looking at a plot of potassium 2-oxide, and it's not normal per se, but it's relatively normal such that if you were to apply a log transform, it's actually approaching something with a right skewed distribution. However, when you're looking at the raw nickel ppm data, you can see that it is very much skewed towards the left. And then when you apply a log transformation, it starts to look a bit more normal. When I get into a new data set, the first thing after the data is QA/QC'd is to look at elements in probability plots to start to understand the structure of the data, element distribution, the different populations, and even deep into analysis, I'll often return to these very simple plots. So how does a probability plot work? They're often used to screen data for non-normality, outliers, anomalies, and multiple populations. The data here is arranged from the smallest to the largest. The percentile of each data value is determined, and then from these percentiles, normal calculations are done to determine their corresponding z-scores. Each z-score is plotted against its corresponding data value, and if the distribution is close to normal, the plotted points will close to a line. Systematic deviations from line indicate a non-normal distribution. A key advantage compared to histograms is that every data point here is visible. So when you're looking at this plot, it's probably one of my favorite because it describes these points quite well. So when you're looking at this, you see this green line over here. So if you had all the data plotting according to that line, then you would just have one population. But here you can see that you have one line here, then perhaps you got another one here. You got another population here, and then maybe the slope of the line changes a little bit here, and then you start to get outliers. So what we're going to say here is that anything really that's plotting along this line, you're going to have below detection limit values, and you're going to just remove them from the analysis. But here I would say that this is one population. This is another population. Perhaps this is a mixed population of the first and the second one. And then up here, you get to more of these outliers. They don't really plot along any slope of any line. So once you start playing with these data and then you start segregating them into groups, and then looking at them with other elements, certain things will start to pop out, and that's where things get really interesting. It's really important to understand how elements are related to each other, but it's also important to be flexible. So you're going to be trying out element combinations and exploring the data. And it's really important always to remember your geochemistry basics and mineralogy to help select these different element combinations. But some simple things that you can start doing would be to look at scatter plots. So like scatter plot in an exploratory data analysis context, these variables are plotted against each other. So maybe you have gold versus silver, nickel versus vanadium. And what you're trying to do here is to identify any unusual structures in the data and then determine the process that caused them. And you're testing a hypothesis that a certain variable influenced the behavior of another variable. You can also use classification diagrams. Here you're going to be leveling up from a simple scatter plot. You can use pre-made classification diagram like the TAS plot for volcanic rock classification. You can also create your own. And these will help to verify field relationships and to provide further geological information. And another one that you could do perhaps would be to create a ternary diagram, which would involve 3 variables that sum to a constant. It's going to graphically depict the ratios of 3 variables and positions of an equilateral triangle, and has applications in geology, such as perhaps in petrology and mineralogy data. So we're going to here just plunge right into an application using some simple plots that I've separated out sulfide from sulfate species by plotting iron versus sulfur. So you can see that over here on the left. And here, very simply, sulfates are going to plot on the sulfur-rich side of the pyrite line, which goes up through here. So here you can see iron on my y-axis. And this is just from a 4-acid, 48-element geochemical data suite that included total sulfur. So my first step here was just to simply separate out, okay, these are likely sulfates, and everything over on the other side of the diagram is likely sulfides. The next step I took was to plot an iron, sulfur, copper ternary diagram, and on here I put nodes for different copper sulfide species. For example, you have here covalite, this is enargite, bornite, chalcopyrite, and then I separate out species based on their trend towards the respective nodes. So for example, over here, I plotted out what I believe to be pyrite. Here, this trend in green would be chalcopyrite, and above it would be, in blue would be bornite. And then in between the chalcopyrite and the pyrite, I call this a mixture of the two. Having used 2 plots prior that were provided in the IOGAS platform, I then decided, based on the requirements of a project that I was doing, that I needed to build my own classification diagram. And that I did just by creating fields based on pyrite stoichiometry, so 1 iron to 2 sulfurs. And I created fields that were, for example, low pyrite, which I said was less than 2.5% pyrite, this moderate pyrite field, say 2.5 to 7.5% pyrite, and then high pyrite, so anything over 7.5% pyrite. So this is a brief tour through some important basic geochemical data interpretation concepts with an example that will hopefully get you inspired to look at a data set. So happy exploring.